In this video, we're going to learn how to implement A pathfinding in Unity. We're going to set up our world in a grid with some areas blocked and implement the algorithm to calculate valid paths. Then in a future video, we're going to apply this same algorithm using Unity dots. Let's begin. Hello and welcome, I'm your Code Monkey, and this channel is all about helping you learn how to make your own games with in-depth tutorials made by a professional indie game developer. So if you find the video helpful, consider subscribing. Okay, so this is what we want to create. Over here is our map with the grid visible, and you can see some black squares which represent the areas that are not walkable. Now in here I have my character, and I can click to tell him where to go. When I click, the path is calculated and he then follows that path. We can enable the debug view in order to see what's going on inside the algorithm. So over here you can see the various values that the algorithm uses, and you can see it looking around for all of the neighbors. After going through the entire process, you can see that it located the correct path. Alright, so this is our goal. Let's get to it. So before we get to the code, let's first check out the theory. The goal of the A pathfinding algorithm is to search to find a path from A to B. So the algorithm already detects walkable and unwalkable areas and correctly identifies the shortest path from A to B. Our map will be grid-based. From each grid position, we can move in all 8 directions. On each node, essentially we have 3 values. First we have the G cost, that is the walking cost from the start node. So for example, to go from this node into this node, it has a cost of 1. And we can also move diagonally, so from this node into this node has a cost of 1.4. Now, in order for our code to work with ints instead of floats, we're simply going to multiply our values by 10. So horizontally we have a cost of 10 and diagonally a cost of 14. Then we have the H cost. This is the heuristic cost to reach our final goal, so it's essentially an estimate to try to reach the goal. Our calculation is simply assuming there are no walls, so moving straight towards our goal. So in here our H cost will calculate going from here to here to here. Again, this is just a basic guess to figure out which nodes to prioritize. And finally, we have the F, which is simply G plus H. So this combines our actual cost from the start, combined with an estimate to reach the goal, and we have our final number. Using this, we can prioritize nodes with lower Fs, since those are more likely to be closer to the goal. The algorithm finally stops when our current node is our goal node. So if we start here, first we check all the neighbors. These are unwalkable, so they are ignored. So he checks this one, then checks these 2 neighbors. Then this one has a lower F value, so it checks this one, checks the neighbors for that one. Then it starts locating that one, and it says that this one is the goal, so we have our path. So here, as you can see, the G cost is constantly increasing, and the F cost is constantly decreasing. Then our path is traced back from the final node into our origin node. So each node also knows what the previous path node was. Then for the algorithm to work, we also have 2 lists for our nodes, the open list and the closed list. The open list is where we have all the nodes that are queued up for searching, and the closed list are all the nodes that have already been searched. So we keep going until we find the current node on the open list, or our open list is empty, so we no longer have anywhere to search, so there's no path. Okay, so this is the theory. Now let's implement it. So over here is my starting scene. Let's start off by making a new C# script. Call this our pathfinding. Now in here, let's get rid of all of this and get rid of mono behavior. And let's make a constructor that receives a width and a height. Okay, now we want to set up our pathfinding in a grid. So for that, let's use the grid class that we created in the previous video. Here is a class. It manages a grid with a certain width and height. Now we created this completely from scratch in a previous video, so go check the link in the description if you haven't seen it already. So using this class, let's go into our pathfinding. And in here, let's create our grid. So up here we define a field for our grid. And now in here we require a grid object. So let's make one. In here, let's make a new C# script, and let's call this the path node. So this will represent a single node in our pathfinding grid. So let's make a constructor. Here, let's receive the normal stuff that we create in our grid. Okay, we have all our basics. Now we're also going to have a int for the G cost, then for the H cost and the F cost. Okay, so these are the 3 values that we need to calculate. And finally, we're also going to have a path node reference for the node that we came from previously. So let's call it came from node. So this is the node that we came from in order to reach this one. This is what we're going to use in the end in order to trace back our steps to find the final path. So now we can go back into our pathfinding, and in here we make a grid of path node and call it our grid. Alright, so just like this, we are instantiating our grid. Again, check the link in the description to see how we made this grid class completely from scratch. So now in here, let's make sure that everything is working. Back in the editor, let's make a nice testing script. Let's make a testing game object and attach the script, okay. Now here in our testing, let's create our pathfinding. Just like that, okay. Finally, let's go into our grid, and here just make sure that we have show debug set to true. So just like this, we should be able to see our grid. Let's test. And if there it is, we have our grid correctly being instantiated. Alright, great. Now let's get to work and implement the actual algorithm. So over here on the pathfinding, let's make our function. This will return a list of path node for our entire path. Let's call this find path. In here we'll receive an int for the start x, for the start y, for the end x, and for the end y. So we're calculating a path from these coordinates into these coordinates. So in here, first let's set up our open and closed lists. And here we also add the start node to our open list, and the closed list remains empty. So to get the start node, we go into the grid, we get the grid object on start x and start y. And we start with the start node on the open list. Again, the open lists are the ones that we're queuing up for searching, and the closed lists are the ones we've already searched. So we start off with the start node queued up and nothing on the closed list. Now let's initialize our grid. So we need to cycle through all of our nodes and set their g cost to infinite and calculate their f cost. So to initialize, we set the g cost to infinite. So int.max value, and then we calculate the f cost. So let's make a function to do that. So back here on the path node, we simply make this. And again, the f cost is simply equals to the g cost plus the h cost. Okay, here it is. Now in order to initialize our list, we also need to set the came from node back into null, so it doesn't contain any data from the previous path. Okay, so now let's begin by calculating the costs for our start node. So the start node.gcost, this is the start node, so the g-score is 0 since we start right in here. Then we need to set the start node.hcost. So in here we're going to have a function, and let's call this calculate distance, since that's pretty much what the hcost is. It's a distance while ignoring all of the blockable areas. So here we have a calculate distance cost. We take an a and a b, and here we just want to calculate the quickest direct path. So we go horizontally as much as possible and then diagonally. So let's go up here to define our basic costs. So here we have the straight cost at 10 and diagonal cost at 14. The reason why it's 14 is essentially that is the mathematical value for a diagonal. So we have a square root of 200, which is 14. Okay, so now we can go all the way down here. And our final distance cost will be the amount that we can move diagonally plus the amount that we have to move straight. So the distance cost is essentially our h cost. So we can go up here in order to set the h cost for the distance cost between the start node and the end node. Okay, so just like this. And finally, we can go into the start node and calculate the f cost. All right, so this is our starting data for our algorithm. And now in here, we're going to have our cycle. So we're going to do our cycle while the open list.count is bigger than 0. So while we still have nodes on the open list, in here we get the current node. And now the current node will be the node on the open list with the lowest f cost. So we're going to make a function to do that. We're going to return a path node, and let's call it get the lowest f cost node. Okay, so here it is. We simply cycle through our entire node list and we get the lowest f cost node. So now we can use this in here in order to get the current node. We pass in the open list, okay. And now the first thing we do is check if this is our final node. If it is our final node, then we have reached our goal. So here we return our calculated path to reach this node. Okay, and let's just define this function in here. It's going to return a list of path node. And for now, let's leave it empty. We're going to make this function later, okay? For now, let's keep going in here. So if it is the end node, then we calculate the path that we took to reach that end node. If it is not the end node, then first of all, we're going to remove the current from the open list. So we're indicating that the current node has already been searched, and we're going to add it into the closed list. Okay, so far so good. Now in here, we're going to cycle through the neighbors of this current node. So let's make a function to get our neighbors. Okay, so here we have our neighbor code. We simply take our current node, then we check the one right to the left of it, if it's valid, so that's why we're checking above 0. So if it is valid, then we add the left one. Then we see if we have a node underneath it. If so, then we add the left and down, and then left and up, and then right, right down, right up, down, and up. So just like this, we have our 8 neighbor positions if they are valid. So we have our neighbor list, and in here we cycle through it. So we cycle through all the neighbors of the current node. Now in here, first we check if the neighbor node is already on the closed list. If the neighbor node is already on the closed list, then that means we've already searched it, so we simply continue. Now if it isn't on the closed list, then we need to search it. So in here, let's calculate a tentative gcost. This is based on the current node.gcost plus the movement cost to go from the current node into this neighbor node. And now with this tentative gcost, we're going to see if this one is lower than the actual gcost currently stored on the neighbor node. So essentially we're trying to see if we have a faster path from the current node onto the neighbor node than we had previously. If we do have a better path, then let's update it. We go into the neighbor, we set the came from node to be our current node. Then we set the neighbor gcost to be our new tentative gcost. Finally, we calculate the new hcost to be the distance between the neighbor and the end node. And finally, we calculate the f value. Okay, so here we have updated all of the values for this neighbor node. And then we simply check if it is not already on the open list. So if the open list does not contain our neighbor node, then we add the neighborhood to the open list. Okay. And that's it. This is our complete algorithm cycle. And now if we reach down here outside of the while, then that means we are out of nodes on the open list. Essentially, this means that we searched through the whole map and we could not find the path. So in here, let's simply return null. All right, so now finally, the last thing we need is simply to implement this function here, the calculate path. So in here, again, each path node contains a reference to the node that it came from. So we can simply use this to retrace our steps. So in here, let's make a list of path node. We start our path off on the end node. Then we calculate a current node, which is going to start off with our end node. And now we're going to do while the current node.camefrom node is not null. So essentially, while the current node has a parent, we're going to add to the path the current node.camefrom node. And then we're going to update the current node to be the current node.camefrom node. So essentially, we're constantly cycling through the parent until we reach one which no longer has a parent, which will be our start node. So again, here we're coming from the end, going back into the beginning. So in the end, we simply need to reverse our path. So path.reverse like that, and we can finally return it. Right, great. So we wrote quite a lot of code here. Now let's see if our algorithm has been correctly implemented. For testing, let's go into our testing script. And in here, let's test it on mouse down. So in here, when we press the mouse down, we get a vector3 for the mouse world position. Here I'm just using a function from the utilities. As always, you can download the utilities for free from unitycodemonkey.com. If you want to make it yourself, here it is. All we're doing is a world camera screen to world point, okay? So we get the mouse world position. Then let's convert this into grid positions. So we go into the pathfinding, we get the grid, and then we get the XY positions, and we pass in our mouse world position. Okay, so now we have an X and a Y that we can use. So in here, let's calculate a path. Okay, so here we have our function. We get the mouse wheel position, convert it into an x and y. We calculate a find path starting from 0, 0 onto our mouse position. If we do have a path, then simply use draw line in order to draw our path. Okay, this should do it. Let's see. Okay, here we are with our grid. Now I can click and we're going to see a path starting from 0, 0 going into the mouse. So let's click right in here and click. And there you go. There's our very nice path. As you can see, go from there, 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 there. Now I can click wherever I want and the path is already automatically calculated. So just like this, we have correctly implemented A* pathfinding. Awesome! Now over here I have prepared a nice script that we can use to visualize the inner workings of the pathfinding. So for example, let's try to move to this square right here. So I click, there's the path correctly calculated. Now let's see how this path was calculated. I can press space to go step by step. So there you go, on the very first step it calculates the f cost in the middle, g cost up there, and h cost down there. So g cost is 0 since this is the start node. The h cost is 24, which is the assumption to get there. So we got 10 here and 14 in here. So we have 24 and the f cost is right there. So now I can press space to go for the next step. And here we go, we start searching for the neighbors. So again, this neighbor has a g cost of 10 since we moved from here to here. So that's 10 and 14 to reach the goal, which is here. So 14 right there. So the f cost is still 24. Now let's check the other neighbors. So there you go, that neighbor, calculate the cost, and that neighbor, calculate the cost. So you can see the blue squares are the nodes on our open list. And now in the next cycle, we're going to start searching from the node with the lowest f. So that means we're going to start searching either this one or this one, but not this one. So I hit space. And there you go. Now this one is red, which means it's on the closed list. So we have fully searched this node. Now we're searching this node. So now we search the neighbors for this one. Search that one, and then we also try to update any other neighbors. Now we go to the next one with the lowest f cost, which is this one. Again, remember this is our goal. So now we check the neighbors on this one. Okay, there it is. As you can see, it calculated all of the new neighbors. And now we keep going. And now we are searching our final node. So the current node is our end node, so we have finished our goal. So we click, and there you go, there's our final path. Go from here to here to here. So with this script, we can easily visualize how the algorithm works. So here I can click anywhere to view an animation of the algorithm at work, and there you go, as you can see, constantly searching for the neighbors until it finds the path. So click in here, and there you go, searching for those, and constantly searching for the neighbors, constantly going from the lowest f cost, and eventually it searches and it finds the goal. Alright, so now with this working, let's add some unwalkable areas. Let's go here into our path node, and in here let's add another field. We're going to make this a boolean and call it isWalkable. Now by default here in the constructor, let's set it to true. And now all we need to do is go into our pathfinding. And in here, when we're inside our cycle, when we're going through here, cycling through all of the neighbors, in here, all we need to do is check if the neighbor node, if it is not walkable, then we're simply going to add this to the closed list and continue. So here it is, very simple. All we need to do is set this to false, and now that node will be ignored from our algorithm. Now over here I have a simple visual script. All it's doing is drawing a quad on certain positions. So where it's not walkable, it's going to draw a black quad. If you'd like to see an in-depth look into how this script works, then check out the Heatmap video linked in the description. All it's really doing is just drawing that black quad. So in order for this script to work, all we need to do is call setGrid in here. So let's go into our testing. In here had a field for the visual, and we simply call setGrid, and we go to the pathfinding and get the grid. Alright, now finally let's make a grid unwalkable by right clicking. Okay, so when we right click, we're simply swapping out the isWalkable on this node. So let's see. Okay, so here we have our grid map. Now let's left click, and there you go, there's the path like normal. Now let's right click, and there you go, that one turned to black, so that node is no longer walkable. So now if I left click in here, in theory it's going to go around this. So click, and yep, there you go, our new path is calculated, and it's avoiding the unwalkable area. So I can block a bunch of these ones, then click out here, and there you go, there's the correct path going around everything. So I can make this as complex as I want, and as long as the path is possible, it won't find it. There you go, just like that. So you can view the inner workings of the algorithm. There you go, it's constantly checking all of those, checking all the neighbors. Now it's trying to go through there, but it finds out that it can't go through, but it's still trying to go until it reaches 146 on the lowest. and keeps going, keeps trying to search all of that, and nope, and it finds through here. So there you go, there's our final path. So regardless of whatever obstacles we place, our algorithm will always find a path if there is one. Awesome. So just like this, our pathfinding algorithm is now working with blocked areas. Now let's just make the map bigger and apply the pathfinding into a unit. Over here I have a simple script to move a unit. It's already set up in order to follow a list of vector 3s. Down here I have a function to set the target position, and it's in here that we're going to calculate our path. So let's go into the pathfinding. And now in here, if we just have one pathfinding in our game, then we can make it a nice singleton so we can easily access it. So here we have a public instance and we're setting it on the constructor. So now using this, we can go back into our character, and in here, let's set the path vector list, and we go into the pathfinding, access the instance, and now in here we want the find path, but we want a version that returns a list of vector 3s. So in here, let's make that. Let's make a function, returns a list of vector 3s, call it find path, and now in here, let's also receive world positions. So we go into the grid to convert our world positions into grid positions. Then we use our normal function in order to find our path. Now in here, first we need to check if the path returned was null, meaning if we did not find a path. But if not, then let's convert our list of path nodes into a list of vector 3s. So we cycle through all the path nodes in the path, and we convert them into vector 3s using the x and y multiplied by the grid cell size. Alright, so just like this, we have this nice function. It takes in a start world position, a end world position, and returns a list of vector 3s that the unit can easily follow. So back in here, we can use find path. We pass in the start position, which is this one, so get position. And then the end world position, which will be our target position. And just like this returns a path vector list. And in here, you can see the handle movement function. If we do have a path vector list, it grabs the next target position. It sees if it's far enough. If so, then we want to move towards it. So we move our position towards our next waypoint index. And when we are close, then we simply increase the index. And if we are past the count, we stop moving. So there you go, very simple pathfinding movement. And now we can go back into our testing. And in here, let's add a field for our character. And when we left click, let's tell our character to go to there. So we set the target position into our mouse world position. Alright, that should do it. Let's test. So here we have our nice unit standing on 0, 0. And now I can click somewhere, let's see it move, click, and there you go, it starts to move exactly like that. Now I click somewhere else, and there you go, the path is always correctly calculated. Now in here, let's add some walls. So add these walls, now go down here. Now let's go in here, and there you go, he goes around the walls. So I can make the map really complex. And now if I click all the way in here, yep, there you go, there he's going through down here, down here, down here, and so on. So as you can see, the unit is automatically calculating the path and moving alongside it. Right, awesome. So just like this, we have our A-star pathfinding fully working. We can calculate the path from any position into any other position. Now the class that we wrote here does work, however in terms of performance it is far from optimal. There are a lot of things down here that we can do to greatly increase our performance. For example, here on get lowest fcost node, in here all we're doing is a very linear search. So the more nodes we have, the worse this is going to be for performance. Something like a binary tree would be much faster. And here on the neighbor code, we're also dynamically identifying the neighbors for every single node. We could improve this significantly by simply pre-calculating all the neighbors as soon as we make the grid. So as you can see over here, we have plenty of ways that we can take this and continue improving upon it in order to make it a proper pathfinding script. Let me know in the comments if you'd like to see a video just focused on performance improvements. Now that this video is done, I'm working on another video where I will take this exact same class and convert it into using Unity docs, so stay tuned for that. As always, you can download the project files and utilities from unitycodemonkey.com. Subscribe to the channel for more Unity tutorials, post any questions I have in the comments, and I'll see you next time.